Alright guys, we're going to switch gears to a brand new chapter and a brand new set of things. Probably some things we haven't seen before. So these are the molecules of cells. Little background, something to kind of think about, is that most of the world's population can't digest milk-based foods. These people are lactose intolerant. That's me too, because they lack the enzyme lactase. This illustrates the importance of biological chemicals such as lactase in daily functions of living organisms. So it kind of breaks down lactose and sugar. If not, you start to feel gross, like that happens to me. Alright, so today we're actually going to introduce organic compounds. We're going to talk about carbohydrates and maybe get into lipids just a little bit. And we'll start on some of those things and try not to go too long. But we've got the next week to cover the rest of this chapter. So, which will be the other two. So we're going to cover nucleic acids and proteins as well. So let's do an introduction of organic compounds. We also need an essential question. Let's see if I can write it out here. As we want to talk about how are the macromolecules of life classified. We'll make it a little longer. Macromolecules. You could say of life if you want to. Classified. You can also leave the out. Doesn't matter. But we just want to talk about how are macromolecules classified. What are those things? Okay, so almost all of molecules in a cell are composed of carbon bonded to other carbons and other elements. Carbon-based molecules are called organic compounds. So this brings us back to that little foldable that we talked about, from chapter 1, chapter 2 in there, is that when we have carbon-based molecules, they're called organic compounds. So the word organic is just referring to it contains carbon. Okay, or it's carbon-based. Okay, by sharing electrons, because it's more of a sharer, tends to do that, but carbon can bond with 4 other atoms, and it can branch up to 4 different directions. So basic thing is simplest one is methane. It looks like this, because we have our carbon in the center, and then we have hydrogen on each end. The whole idea is this is the very simplest that you can do for organic compounds. Everything else, we can take it out here, add another carbon, add hydrogens, add other carbons. The whole thing is that the possibilities here are endless. Okay, but we have 4 covalent bonds that are linked to 4 hydrogen atoms to the carbon atom. Each of the lines in the formula of methane represents a pair of shared electrons. So we could do the octet rule, 1, 2, 3, 4, 5, 6, 7, 8. Good. So carbon's happy in that sense. You could look at it this way. This is kind of the 3D model of that. So the whole idea is the hydrogens will try to get as far away from each other as possible. So it makes a nice kind of what they call tetrahedron shape. Okay. Methane and other carbons are composed of only hydrogen and carbon are called hydrocarbons. How creative is the naming on that one? Hydrogen carbons. It's like, what is it? I don't know. I'm thinking, see, this is how old I am, is my age. I'm thinking like Benifer. Or what is it? Is it Kimye? Is that what they do? Like a Kim and Kanye thing? That's kind of what the hydrocarbons have going on here. Hydrogen carbons, we just stick the name together. Scientists are the original name putters together. That's my thought anyway. So carbon with the attached hydrogen can form chains of various lengths, like any kind of length that you're possibly thinking of. A carbon skeleton is a chain of carbon atoms that differ in length but can be straight. So it's like carbon hooked together like this. But we can also branch it, like put another carbon out there. Again, all the rest of these would be filled in with hydrogens. So we get the idea of where we're going with this one. Okay, hydrogen. Okay, so that would be at the other spots on this too to fill it in. But it can also be in rings. So a lot of times you'll see carbons in these kind of, we call aromatic rings. They end up in like little hexagons, which they call a ring. All right, so here's some of the examples that we would see. It's a whole organic chemistry naming system. We could go through it if you wanted to, if you're really into that kind of thing. But nonetheless, you can see there's some straight chains. And we've even got some double bonds thrown in there. We've got some fours. We've got branched here. We've got the ring structures, lots of things. You don't need to know those, but just to show the diversity of the carbon chains. Compounds with the same formula but different structural arrangements are called isomers. So that is a key term to know. I don't know what just happened there, but we have isomers. Same formula but different arrangements. So you'll have a couple of these. There's some structural, some geometric, some enantiomers. The whole thing with this is fascinating that we could talk about, but the idea is that like your body will recognize one mirror image because these are mirrors, but not the other. So being oriented a certain way is super, super important. Oh, so important. Not going to get into it too much because I know we want to move forward, but the whole idea of isomers is just fascinating. All right, so the unique properties of an organic compound depend on the size and the shape of the carbon skeleton. So that's just kind of the chain or the rings. And the group of atoms that are attached to that skeleton. So although we put carbon and hydrogen together, you can also put in an oxygen. You could share with, sometimes there's a sulfur in there. We can have nitrogen. Just lots of things can be attached to that. Some examples is the sex hormones, testosterone and estradiol differ only in groups of atoms highlighted in this figure. So take a look at this. Here's testosterone. And we'll have like a methyl group here, and then a double bonded oxygen here, and we only have a hydroxide group here. So just some tiny differences, and those little tiny differences alone cause the vast differences between testosterone and estrogen. It's crazy. Right? So that's the whole point of chemistry, is that we have these little things called functional groups, and they help give molecules characteristics in different ways. So the functional group, just a different little attachment, can make the whole function of that molecule completely different. It's so cool. That part, it's hard to learn, but that part of chemistry is cool if you step back and kind of respect it, that just these tiny differences can make this massive impact on the bigger scale of like a whole animal. Okay, so the 5 groups are polar. So compounds containing them are typically hydrophilic. So if we have some polar ones, we'll talk about, they'll be hydrophilic, or soluble in water, or water as in hydro as in water, and phil as in love. So water loving, or soluble in water. Oh my god, I keep dropping my pen. There you go. Okay. So there's a 6th group called the methyl group, and it contains a carbon and 3 hydrogen. It's nonpolar and non-reactive, but it still affects the molecular shape and function. Okay, I won't ask you to know any of these. We'll see a couple as they come up that are really, really important. You'll see hydroxyl groups. They're usually involved in alcohols. They're kind of defining characteristics of alcohols. We have a carbonyl group, which we'll see. The carboxyl group we'll see a little bit later when we start dealing with amino acids. Same with the amino group. Phosphate groups are going to be super important as we go along, and then there's the methyl group. So you don't need to memorize these, but the whole point is, regardless, we're going to see these a whole lot. So it might be worth at least looking at. All right, so again, I'm not going to go over them too much. You see the pictures. You can go through the whole thing on that one. I don't need you to memorize those. We'll just identify them as we go along. Okay, here's a big one to note. So this is really important to start with, is that there are 4 classes of molecules that are important to organisms. We'll have carbohydrates that we'll talk about today, and lipids. We'll also have proteins and nucleic acids, and these 2 are really, really interrelated. Actually, they're all kind of interrelated, but those 2 in particular have a whole setup. Okay, so these are our kind of, I give them several terms. So they're organic molecules because they're all going to contain carbon. They're also macromolecules because, they're going to be large. And we'll also call them polymers. So anytime you see one of these words, we're still referring to these 4 classes of molecules. All right, just to give you that one more time, the 4 classes of biological molecules contain very large molecules. So we call those macro, as in big, it's on that root word, or large molecules, because they're massive relatively. They're also called polymers because they're made from identical or similar building blocks that are strung together. Those building blocks are monomers. So let's look at some other root words here. So mono means one, poly means many. So the whole idea here is that one mers will make up many mers. Yeah, I don't know what the mer part stands for, but that works for us. So we'll have monomers or one mers that make up polymers or polymers, many mers. Okay? Okay, so this is a good place to stop. We're at 10 minutes, so take a break here if you need to. You know, go get a snack, go to the bathroom, come right back. So monomers are linked together to form polymers through dehydration reaction, which remove water. I usually call these, so there's another way, the older term is dehydration synthesis, which I think is more descriptive. We'll look at it in just a second. Okay, but dehydration synthesis or dehydration reactions actually link them together, where polymers are broken apart by what's called hydrolysis or hydrolysis. So hydro will be water and lysis is to split. So things will be split apart through hydrolysis or hydrolysis. Again, we're not super creative with the naming. We're just taking other parts of words and sticking them together and then acting like it's a new thing. But the words and the kind of phrases here want to tell you what's going on. You just have to be able to kind of tease it apart. So these reactions are mediated by enzymes, which are specialized macromolecules that speed up chemical reactions. These are going to be really, really important when we get to kind of Unit 4 and we start talking about cells and what's going on. And actually, we'll do it in Unit 3. So a little bit in Unit 2 and then a little bit in Unit 3. More there. So a cell makes up a number of polymers from a small group of monomers. For example, proteins are only made from 20 different amino acids. DNA, your whole DNA is built from just 4 kinds of monomers that are called nucleotides. So the monomers used to make polymers are essentially universal, as in every kind of organism is going to use them, all the way from like the smallest bacteria all the way up to a human. Like that one? There you go. There's my doodling for you. Okay, so here's the dehydration reaction, or dehydration synthesis as I like to call it, because if we take a polymer and sort of an unlinked, what happens is we're going to make a water and then we're going to lose it. So think about it when you're dehydrated, you've lost water, you don't have enough. So it's a dehydration or losing water. Lose water. So you literally lose the water and then you add those together. So it's dehydration and then we're synthesizing or making a longer polymer. Okay, so that's why I like to call that one dehydration synthesis. Let's see if I can write it out real quick. Dehydration synthesis. They're not short words, but they are descriptive. Because the word synthesis means to make. So we're going to dehydrate and lose the water and then make a longer polymer. All right, so hydrolysis is the other one. So hydro and lysis. So hydro is talking about the water. So we're going to need to add in the water. And then we're going to lysis or split the polymer apart. So lysis means to split. And we'll see that come up with some other kind of biological terms as well, especially in cells. So that one's helpful to note. All right, let's start with some carbohydrates. Let's get through those. And you've probably heard them and can think about them. People say, watch your carbs. Maybe you guys don't think about that as much because you're young and your metabolism is still wonderful. And I just think about sugars. My metabolism slows down, I get fat, and that's how adulthood works. Kind of, just kidding. But anyways, carbohydrates are sugar molecules. So a small sugar molecule would be its monomer, and it can make some really large polysaccharides. So let's talk about what that means. Again, the words are trying to tell you what they mean. So mono means one, and the kind of root word saccharide means sugar. So the monomer here, which I'll give you that, we're going to make a table eventually, but the monomer here for carbohydrates is a monosaccharide, a one sugar. And it's going to make up a polysaccharide or a many sugar. One sugars make up many sugars. Pretty easy. Okay. Some of our examples of monosaccharides or one sugars are fructose, glucose and honey. All right, so honey, these little guys will deal quite a bit with monosaccharides. They protect it with all their might. It's fabulous. So monosaccharides can be hooked together by dehydration reactions. So if we're building it, we have dehydration. They'll help us build more complex sugars and polysaccharides, or many sugars. Okay, so if there's nothing else you get by the whole thing is when you put stuff together, it's dehydration. When you break it apart, it's lysis or hydrolysis. Okay, so the carbon skeleton of monosaccharides vary in length. Glucose and fructose, the kind of basic, simple sugars that we're going to use the most of, are about 6 carbons long. Others have 3 to 7 carbons, it just depends. But monosaccharides are really, really important to fuel cellular work. This is why you eat, because we have those basic sugars get broken down through hydrolysis, and then we're able to use those to get energy. So we use those as raw materials to manufacture other organic molecules that we can use. Okay, so here's sort of what glucose and fructose look like. You don't need to get too invested in their structures. We'll see them as we go along. Many monosaccharides, or one sugars, form rings. So they form that kind of like hexagon structure. Just let it be. So the ring diagram may be abbreviated by not showing the carbon atoms at the corners of the ring and drawn with different thicknesses for the bonds to indicate that it's a relatively flat structure. So, you know, we can get all kinds of cool things out of it. Like you can see the structural formula where we put the carbons. They can show you that there's like, it's kind of a 3D thing. So this part would be facing you. Then you get the really simple one where it's like, I drew a hexagon and you're supposed to know what that is. Again, if you're interested in science stuff, this is the kind of organic chemistry classes you take in the future to know what those mean. But at least you've seen it a little bit. Okay, so 2 monosaccharides will come together to form a disaccharide. But if we add 2 one sugars together, we get a di, which means 2. We make a 2 sugar. Such creativity in naming. Not, right? Again, if we're putting things together, if you're putting them together and you're linking them or bonding them or making them larger, it's a dehydration reaction or dehydration synthesis. Okay, the disaccharide sucrose, which is kind of like your table sugar, actually takes glucose and fructose. Just so you kind of see that. All right, just so you see what it looks like. How delightful. Again, we dehydrate or lose a water, and we synthesize or put that thing together. That's all I want you to get from that. Most sodas, here's a little connection for you. Most sodas and fruit drinks, reverse it here. Most sodas and fruit drinks contain high fructose corn syrup. Ooh, the words today. Fructose is actually sweeter than glucose, and to make high fructose corn syrup, atoms are rearranged to make this kind of glucose isomer fructose. Crazy stuff. You don't have to really note it, but this is a good connection. You don't need to write notes over this. High fructose corn syrup is used to sweeten a lot of beverages, and it contains about 55% fructose and 45% glucose. So the mixture is about the same proportion as sucrose, like what you're kind of like cane sugar, or sort of what they call table sugar. Okay. So most scientific studies have shown health consequences associated with replacing fructose or sucrose with high fructose corn syrup, as in we've not shown those. I don't know. I just think they taste different. Like if you have a regular Coke, that's cool. And then if you have like the Mexican Coke that still has the cane sugar in it, they taste totally different. I'm like, that commercial could tell me all day that those things taste different, or taste the same, but they don't. I'm just saying. There was a commercial about it. I may be old, whatever. Although high fructose corn syrup consumption has declined somewhat in recent years, obesity rates continue to rise, and probably the amount of sugar we're eating is not helping. It's so delicious. That's the hard part, right? So good health is promoted by a diverse diet of proteins, fats, vitamins, minerals, complex carbohydrates that we'll talk about, and exercise. I always say motivate yourself to lead a family activity where you can enjoy some, walk and talk or something. That always helps, because I know we sit down a lot. So then you can see it on a Coke can, the high fructose corn syrup. All right, polysaccharides, something a little different. We'll talk about it quickly. The polysaccharides are many sugars. So again, many sugars. Okay, many sugars that are macromolecules. So the polymers are composed of thousands of monosaccharides or one sugars. Their big function is for storing molecules and for structural compounds. So they kind of hold up structure and they can store important molecules for us. So starch is a polysaccharide. It has lots of glucose monomers. It can be used by plants as energy storage. Another example is glycogen. It's a polysaccharide or mini sugar. Again, just glucose monomers and energy storage again. So how are these two different? Starch is found in plants. Think about it. You have a starchy potato, makes delicious French fries. Okay, a little different for animals. Can't store things in the starch variety. We got to store it in the glycogen variety. Slightly different. Cellulose is a polymer of glucose. It forms plant cell walls. We actually can't digest those at all. We can talk about that plenty later. Another example is chitin. That's chitin. It's a polysaccharide or mini sugar. It's actually in the insect and crustacean exoskeletons, or kind of the hard parts on the outside. Cool thing that we'll talk about with evolution is it's actually found in the cell walls of fungi too. So kind of gets to this kind of interesting evolutionary connection about where fungi fit in the whole tree of life. Fascinating stuff. So you can see what starch looks like. It's just repeated glucose over and over again. Glycogen's basically the same, but it'll branch off in some different directions. It's better for animal storage. With cellulose for plants, part of their cell wall, it's just this whole kind of starch compound, but then they're in these sheets held together again by hydrogen bonds. You see all those little dots there. So it's definitely a hydrogen bond. Gives them these interesting sheets and structures. Okay, polysaccharides are usually hydrophilic, so you could think of like bath towels or even like paper towels, for example. It's still part of that. It's made of either cotton or something similar to that, which is mostly cellulose, and so therefore it's water absorbent. So that's why we're able to draw the water up through paper towels and things like that. Kind of from our last little experiments that we looked at. Okay, great time to take a break. We're at 22 minutes. Realize I'm moving quickly, but take a break. Do take a look back at your notes. Write some questions on the side for yourself so you can know where you're at. Maybe write a summary over the carbohydrate section. Just something real basic so you can get that together. Okay? Take a pause, take a breather, think about some things, and then come back to me. All right, let's talk about lipids. This one will hopefully be shorter enough for us to kind of get through, but lipids are really interesting. They're kind of our grab bag. They're going to have some interesting things. So I'll tell you first of all, they don't really have a monomer. So we'll say no monomer, because we're going to have a variety here. Their basic thing that they have in common is that they're water insoluble or hydrophobic. So phobia is like a fear, so they call them water fearing. These are important in long-term energy storage. They contain twice as much energy as a polysaccharide. So your sugars are for quick storage, or quick energy often, but these guys will give you long-term energy. It takes a lot longer to break them down, which is also one of our storage things. That's why you get a little older, your body starts storing things for energy, and that's what happens. It consists mainly of carbons and hydrogen atoms, and they're linked by nonpolar covalent bonds. Again, nonpolar things don't get along with water, so that's our water-fearing business. Okay. Lipids differ from carbohydrates, proteins, and nucleic acids because they're not really that huge, and they're not built from monomers. So that really is a key component to know. So not really monomers, and they have a huge deal of variety in structure and function. They can do a lot of weird things, which is cool. We need that. Just their key kind of connecting point is that they're all hydrophobic. Okay, so we'll consider the three types of lipids: fats, phospholipids, and steroids. So a fat is a large lipid made of two kinds of smaller molecules, a glycerol and a fatty acid. Let's see if we can get a look at it. But A fatty acid can link to glycerol by, oh my goodness, if we add things together, it's still a dehydration reaction or dehydration synthesis. So if we're linking or adding, it's a dehydration synthesis. If there's nothing else that we get from the next two lectures, it's dehydration synthesis puts it together. If we need to break it apart, it's hydrolysis. Okay, so a fat contains one glycerol linked to 3 fatty acid chains. So fats are often called triglycerides because it's a glycerol with 3 fatty acids. Isn't that fun? So here's sort of what you see. It's a glycerol and a fatty acid, which is just a long chain here. And we can take and build a water. We can lose that water through dehydration. And then we put it together. Okay, so that's, again, a triglyceride because there's 3 fatty acids. So we call it a triglyceride. Oops, glyceride. So the glyceride is up here, but then we have tri for 3 of those. So that's a little weird in the naming, but we'll take it. Okay, there's a couple of things to note about saturated fats versus unsaturated fats. So saturated fats are usually like you find them in kind of meat or you find them in butter. These guys are the ones that are solid at room temp. Solid at room temperature. Okay, and then we have unsaturated fats, which would be liquid at room temperature. Okay, so we'll talk about that here. Some fatty acids contain 1 or more double bonds, and that makes them an unsaturated fatty acid. So if you have 1 fewer hydrogen atom on each carbon of that double bond, the saturated here means that it's saturated with the greatest number of hydrogens. So saturated has like we're the most amount of hydrogens we can have. The double bonds, so less than that. Okay. So hold on. Saturated means greatest number of hydrogens. Excuse me. If we have unsaturated, it means not the greatest number of hydrogens. Okay, there we go. So they'll have 1 fewer hydrogen, and the double bonds can cause kinks or bends in that carbon chain. It actually prevents them from packing tightly together and solidifying. Okay, here we go. The fats with the maximum number of hydrogens are called saturated fatty acids. There we go. Okay. Always, I'm serious. We value correct information over any hurt feelings. If something doesn't look right, you gotta tell me. Okay, I know you're not here to tell me. I'm sitting here doing these things alone in a room. You couldn't tell me, but I'm just saying after the fact, you're still welcome to let me know if there's an issue. Because I barely got that poor slide out. My goodness. All right. So unsaturated fats are oils. There we go. And animal fats are saturated fats. Okay. We have this other stuff called hydrogenated vegetable oils that are unsaturated fats that have been converted to saturated fats by adding hydrogen. So it's hydrogenated because I added hydrogen to it. Turn hydrogen into a verb. So the hydrogenation creates these trans fats, which are really not, just basically not what nature intended. So the body doesn't really have a way of dealing with them because it doesn't know how to observe those. All right. Phospholipids are the major component of cell membranes. We're going to talk about these a lot coming up in the next unit. So it'll come up. They're structurally similar to fats because they contain 3 fatty acids and a glycerol, just like what we saw. But then a phospholipids contain 2 fatty acids attached to a glycerol. So this one's going to be 2 instead of the 3. All right. We're also going to have that phosphate group up at the top, which is why it's called a phospholipid. This is a lipid, and then we've added a phosphate group to it, so we have a phospholipid. That's another one of those, like, chemie names or whatever. I don't know. Who are people talking about these? I don't even know. Don't update me. I don't want to know either. It's better this way. Phospholipids cluster into a bilayer of phospholipids. There will be some hydrophilic heads, and so these are actually water-loving, and they'll kind of get in contact with the water environment inside the cell and kind of outside of the cell. Again, we'll talk about this in a lot more detail later on, but at least so you can sort of see what's happening here. The hydrophilic tails will also cluster towards the center of the bilayer because these two kind of like things with hydrophobic tails will line up towards each other. So you see that here. These are our hydrophobic tails, and both of these little squiggly guys line up together. The hydrophobic heads both get along with water, and so they're going to take the kind of watery environment on both the inside and the outside of the cell and just be happy with that. Really the last things that we'll talk about as far as fats or lipids go is these steroids. So steroids are the lipids where the carbon skeleton is about 4 fused rings. Cholesterol is actually a steroid, and it's a common component of animal cell membranes. It's a really important one for helping make sure that cell membranes still continue to move. A starting material for making steroids includes back it up. Cholesterol is a starting material for making steroids, and that includes the sex hormones. Dear God. All right. Cholesterol. That's cholesterol right there. Okay. Sort of what it looks like. You've got these 4 fused rings, and those are going to be an important component for helping to make the testosterone and estradiol. Quick connection, we have anabolic steroids, so those are those kinds of synthetic variants of the male hormone of testosterone. Unfortunately, some athletes will abuse them, and there's some serious consequences there, like violent mood swings, depression, liver damage, cancer, high cholesterol, high blood pressure. The violent mood swings is the whole roid rage thing where they're on these steroids and they're raging out. It's just not a very general good look. And having been an athlete, I knew plenty of people that did anabolic steroids, and it just was a damaging thing for their career. So we kind of like to keep things nice. All right, so that's this section. I know we move through a lot of things kind of quickly just to get the introduction and to keep our lectures close as we can to 30 minutes. So if there's anything that you don't understand here because we're on a new material, please email me. Please come by tutoring times. Come find me. Ask questions. We want to make sure that we get this one because this is a big one moving forward that there's parts of it that the STAR test really likes to ask about. So look through it, talk to me. If you have questions, ask them.